So right now we're going to look at how significance tests are related to confidence intervals. So even though it doesn't show it on the learning objectives, these things are connected to a confidence interval, and so we're going to look at that. And then the next video will actually start 9.3.1, and then we'll get back to this powers of the test. So I'm going to quickly remind us about the steps for carrying out a significance test. And in the last couple of times we've talked about our 80% free throw shooter, we were assuming, we were making a claim that they were going to be lower than the 80%. We're going to actually change our alternative for this particular example to, he's just not an 80% shooter, so it's different because I'm going to ask you to look at a two-tail test. So when we run a significance, we're trying to find if there is convincing evidence that the actual proportion of three shows is different than what they made in the long run. Now he's saying he made 80 in the long run, but we don't know if that's necessarily true. So P sub 0 is the proportion that we are using for our null hypothesis, and it's the proportion that we use when we create our distribution to compare the alternate, compare the statistic against to decide whether we reject the null and accept the alternative. So I wanted just to go quickly through a significance test because some people aren't as clear on it. We always have to check our conditions before we can go ahead and do anything. We need to check to make sure that the data was collected randomly. In this case, he did 50 shots. And 10% of the sample can't be more than 10% of the population. Of course, he's taken more than 50 shots in his life, and large counts means that he had at least 10 successes and 10 failures. And given an 80% out of 50, he would have 10 and then 40. So that's taken care of. To run a significance test, we need the distribution for the null population, for the null expectation, which in this case is 80. So I went and we've done this with simulations, and we're also have looked at it with normal distribution. And since the large counts is meant, we can go ahead and create a normal distribution with the P being the middle, and then you calculate the normal distribution with your square root of P minus 1 minus P all over N. And I've created that distribution for us right here. And we're interested in finding out if the probability that here he got a 64, which is about there. We're interested in this probability. But since we're interested in both whether he's less than an 80 or greater than an 80, we're going to go ahead and look at that symmetrical on both sides. So how we're going to find this, instead of eyeballing it, we're going to go ahead and find the Z for this one, and then we're just going to find the probability and then double that. So here's how we find the Z again. We're going to look at the statistic, and then the proportion, and then here's our standard deviation again, and that gives us a Z. In this case, the Z works out to be, I didn't even include it here, it works out to be negative 2.83, which when we find the p-value for that, we get 0.023, and doubling that, we get 0.046. So because the p-value of 0.046 is less than our alpha of 0.05, we reject the null. We have convincing evidence that the shooter does not have an 80% free throw percentage. So what we're going to look at right now is the connection between this alpha of 5 and a 95% confidence interval. So here's the connection to a confidence interval and a significance test. So if we're looking to find whether a two-sided test falls underneath our 5% alpha, the 5% alpha would be the sum of those two tails of 2.5 and 2.5%. And if our particular thing of interest. In this case, it ended up being down here. So it would be this and this. It's less than our alpha. And that gives us convincing evidence that 0.64 wouldn't happen by chance. The flip side of that is doing the confidence interval. And the confidence interval would go ahead and take the data itself, the 0.64, and it would build a 95 confidence interval. Once again, here's our 5 in the alpha, and then that aligns to the 95 in our confidence interval. We would go ahead and build that confidence interval for the 0.64. So this 0.8, we would build it for the 0.64, and that would give us the range of values that would we'd be 95% sure was a plausible interval. So we're going to go ahead and remind yourself how that's done, how they're connected. We found out when we did our significance test that we rejected the null because our p-value was less than the 5%. Another way of looking at convincing evidence is to go ahead and build the confidence interval from the p-hat, in this case, of 0.64, find that plausible value, set of plausible values at a 95% confidence level, and see if 80 is in there. And if 80 is not in there, that's another set of evidence. Plus, it gives us a really good sense of what they actually are, if assuming that they're what kind of shooter they actually are. So the way we do our confidence interval, we would have to check our conditions. We've already checked our conditions, and so we don't have to do it again. And then we go ahead and take our p-hat, our z for that confidence level, and we're going for a 95%, so that's a 1.96. Then we run our standard error formula, and we end up with a statistic plus or minus the 0.133, which is the margin of error. And remember, we can write our intervals in parentheses like that. And then we're done. We can also communicate our conclusion, which is we're 95% confident the interval from 0.507 to 0.773 captures the true proportion. So putting this in the visual of a really sad-looking normal curve, let me try that again. Putting this in the visual of the normal curve, here's 2 standard deviations away and 2 standard deviations up, and we get from 507 to 0.773. We're confident that 95% of the intervals will capture the true proportion. And notice, in this interval, 0.8 never shows up. So that's another way of checking to see if there's convincing evidence for the null. And in this case, there is not.